that we look at. Okay. We started by ideal and real gas because you cannot talk of gas laws without differentiating those gases obeying the law and those gases that do not obey the law. Now, in exam, there are conditions in place for a real gas which ordinarily will not obey gas law. But we have two conditions for the real gas to obey gas laws. But naturally, ideal gases obey gas laws. But we don't have anything ideal. So what we normally do is that the real one we have, we try to make them ideal. So that is the introduction. Now we enumerated the properties of ideal gas based on kinetic theories. Okay? We stated 5 of them. Finally, we ended by saying, for you to make a real gas to obey gas laws, it should be under, normally it should be under, is it high temperature or low temperature? Is it low pressure or high pressure? Low pressure. That's how we did it. Okay. Now, for gas laws, I will not just waste time. Because I was seeing a qualitative analysis today, maybe starting it. Everybody knows Charles Law, abi? Charles Law. What is he saying? Full stop. What else? This is Charles Law. So, but the temperature must be in which unit? Kelvin. Because normally the examiner will give you this thing in Celsius. You calculate from today till tomorrow, you will not get answer. So, but first of all, you have to put it in the form that Kelvin is equal to what? Okay? That is Kelvin for you. But Charles' law, it has some limitations. Charles' law, we have some limitations. You are familiar with this graph, Abby? Okay. Okay. Now, but we know that at 0 degrees Celsius, that if you are dealing with water now, I mean vapor, at 0 degrees Celsius, what happened? Eh? What happened if you are dealing with vapor? What happened at 0 degrees Celsius? Eh? Hey. Don't worry, I don't even want to go deep. I just want to pinpoint exam points. As you're looking at this graph, do you know what it means? Negative. At 0 degrees Celsius, this gas say have a volume up here. Do you understand me now? If you can explain graph, you are plotting volume against what? Temperature. So which means at a particular volume, there is a corresponding what? temperature. Now, at this particular volume, temperature is what? 0. Now, as we are moving down, what happens here? Volume is what here? 0. Is it possible? That is the problem. It's not possible now for you to say that the gas we are measuring does not exist anymore. Because at this point now, we now have minus what? 7. Because after 0, what do we have again? Minus value. So we have crossed 0. It is now minus. Of course, the temperature of your freezer, is it 0 or minus? It's minus. So the minus will keep on increasing as far as the freezer is on. So some gases will not freeze. Gases like what? Don't worry. But just know that at this point now, our problem with Charles law is that volume is what? 0. Which is not possible with what? Real gas. Real gas cannot be 0. Can volume of air be 0? No. Do you understand where I'm coming from now? Yeah? So from here to here is now minus 273. So from here to here is our problem with what? Charles law. So if you want to convert, it means that if you are dealing with Celsius, Celsius started from 0 to what? 100, okay? It doesn't recognize all these things. Because you have two SI units for temperature. What are they? Celsius and what? Kelvin. But because Kelvin go far beyond 0, it means that if you want to use Kelvin, just add what? 273. Okay? I don't want to go far. It is not necessary because for your jump, when here gawa far, it will be a waste of time. Because there are things you need to know for the exam. So for now, just know that the reason for adding this thing is because we are dealing with what? Charles law. Which extreme points are what? Minus what? 273. And what? 373. Okay, what did I? 273 to what? 370. So just take it that way. So, but the main thing in Charles law is this. Take this formula. That is Charles law. So in JAM, nobody is going to ask you to state Charles law. No. The only thing that calculates this, when this one is what? That. That's all. Now, there is one problem you are going to encounter here. Why calculated in JAM? It might not appear in WAEC. You know, we have a gas can be dry. It can be wet, Abby. Is it wet or moist? Moist, okay. That is, if you collect gas over a sea, you know what I mean by over a sea? They can have a river or an ocean. You collected a gas. That gas is a mixture of what? Vapor and air. That's what I mean. But if you go to desert and collect a volume of air, it might be dry. Do you understand me now? That's what I mean. So which means you now check the equation. If the equation is dry or wet, then if it is dry, they will now give you the pressure, the partial pressure of the what? Vapor. I will explain by example, don't worry. Let me start again. If you're not dealing with a dry gas, the equation will state it. In that case, if maybe this is a container now, and total pressure here, we have not done pressure law, but let me just try to explain a bit. The total pressure here might be 700 millimeter mercury, okay? Total. But inside this container, I thought I was collecting only oxygen. But we have what? Vapor. Do you understand me now? This is no longer dry again, oxygen. Because of presence of what? Water. So anything you are calculating, you must accommodate this person. Because this one has a partial pressure here. This one also have what? A partial pressure. So in the exam, they will give you the vapor gain pressure. That's what we call vapor gain pressure. They will give you the vapor pressure of this water. So that if you're not telling me P1, you're going to must subtract what? Partial pressure of what? Water. What I mean now, if it is volume, you supply the what? Partial volume of this water before you go on. I know you don't understand, don't worry. We do by example. Yeah. So this graph represents which law? Charles' law. Thank you very much. We are done with Charles' law. He says, hey now. Check out what. This is not a high yield question. Oh. See, in chemistry, I know high yield point when I see it. Like when we are treating solubility, I spend a lot of time because it's a high yield what? Point. Even when we are treating a pH, I spend time because it's more of a high yield point than this one. That's what I mean. Where we spend much time now is when we are doing general gas what? Equation. It's of more important than just Charles' law. Understand me? So if I'm saying Charles' law, by now everybody never go to SS1 and SS2. Otherwise you shouldn't be here. So they must have taught you that in Charles' law, that volume is directly proportional to what? Temperature. Is that what you want me to start doing? No. Somebody has to go, yes. Once over the law, I now know where I should start. Before I say, you want to go? Non kurama kuzima wada afia. One can SS1. We are in SS1 now, so listen. Volume is what? In Kelvin. Now, what does it mean? Let me use kinetic theory to explain it. Because I know as far as JAMB is concerned, they will not be asking you all these straightforward questions. You should know kinetic theory very well. So how do we explain this kinetically? You remember when we said that the gas we are talking about is made up of what? Particles, okay? And those particles, they are in constant what? Motion. That motion is as a result of kinetic energy, okay? And increase in what leads to increase in kinetic energy? Increase in what? Temperature. Remember, temperature, heat, they are related, okay? They are related. But the difference between them, that if you are talking, who can differentiate between temperature and heat? We did it last time. Who can? Kinetically. Who will differentiate? Eh? I want to know. Eh? They are afraid of Mike. Then people are not seeing your face. Just talk. Because I will get annoyed if you have forgotten it. Because I know. Last time I told you to erase, that is, clean everything we did that time. But remember this one. I said it. And I said that heat is what? Total kinetic. Okay, you know it. Total what? Kinetic energy. It's different from total internal energy. I hope you know. Because we have enthalpy. You know we have enthalpy. And we have entropy. And we have heat. Yes. If I'm talking of enthalpy, somebody might say in total internal what? Energy. Heat inclusive. But now I'm talking only about what? Heat. Which is total what? Kinetic energy. And kinetic energy means energy of any particle in motion. So if a particle is not moving, kinetic energy is what? 0. But total internal energy might not be what? 0. Or is it? You understand what I mean? If, as I'm standing now, if I'm a vegetable, sorry, I don't want to be a vegetable. You know what vegetable means? Eh? Brain dead. Yes. Brain dead. You are not. Forget about that one. But if somebody is not moving, or if a particle is not moving, kinetic energy is what? 0. But remember, total internal energy is not what? 0. We'll see come to that when we'll be doing Kafia. I will remember. Old age, I beg you. Okay. So heat here is just total kinetic what? Energy. Why temperature is what? Average. So we are trying to link it here. The more kinetic energy of the particle, the more violent they move up here, the more they collide with the walls of the what? Container. And if they are colliding with the walls of container with higher frequency and higher force, there will be expansion up here. Do you understand what I mean? If I don't say, I go SS1. Assuming that this is a volume now, and I have particles here. These particles, they are what? In constant what? Motion. If I increase the heat or temperature, the motion will be what? Violent, more energetic, hitting this container more often. Do you understand me now? More often means the frequency of the collision with the walls of the container will do what? Increase. The energy of the collision will also what? Increase. Because of that, this container will do what? Expand. You want to get now? So which means more heat, by implication, more temperature. What happened? More volume. You know what I now? But something must be constant. That is what? Pressure. You know why pressure is constant? The expansion is because it wants to maintain the pressure. Let me give instances now. Instance. As this thing it is now, if this container is not expansible, what do you think will happen? It will burst. Okay? That is, this, you have increase in volume because the container is what? Expansible. The container can expand. Why is it expand? To accommodate the extra pressure. The extra what? Pressure and volume. Now, but if the container cannot expand, you notice something. The pressure at the walls of the container will be what? Increasing. Increasing. Until the walls of the container, when it can no longer withstand the pressure. But if you make the pressure constant, it means that there will be no increase in what? Pressure. If the pressure increases, what happens? The volume will do what? Increase. To mitigate the what? Pressure. What are you meaning? Yeah? What are you? Hey. SS1. SS1. Well, let me repeat it now. The reason why this volume is increasing is to avoid increasing what? Pressure. Is to do what? Simple. Because if it did not increase, the container will do what? Burst. Because of what? Increase in pressure. Do you see why pressure is constant? So the volume can only increase if pressure is what? Constant. That's what I mean. So Charles' law is obeyed only when pressure is what? Constant. So kinetically now, if I am to explain Charles' law, it means increase in kinetic energy, increase in heat or temperature leads to increase in what? Kinetic what? Energy. And increase in frequency of collision of the particle with the walls of the what? Container. It is that increase in frequency. You see, this gas particle now is colliding with the walls of this container. What I mean now? If the temperature is, let's say, 100 Kelvin, they will be moving slowly, Abby. They will be moving what? Slowly. So they might be colliding with the walls of the container maybe 10 times in a minute. But if I increase the temperature or heat, they will move what? Faster. And start colliding like 100 times per what? Minute. Do you see the frequency now? So if they are colliding more often, it means that the walls of the container will do something to accommodate it. Okay? What would it do? Expand. So that instead of previously, you are traveling 5 minutes to hit me. Now, I have to increase distance to what? 15 minutes of 6. Look at what I mean. When the temperature was 20 degrees Celsius, the frequency of the collision, let's say, is 20. Do you understand me now? Now, if I increase the temperature to 50, the frequency of the collision will also increase to what? 50. And the more often you hit the container, the expansion you are experiencing, do you understand me now? Then I want to bring it down to maybe ordinary man's understanding by saying that if from here to here is 5 meters now, it will be easier for this gas particle to collide with the container, okay? Like 100 times. But if I expand this container, what will happen? Instead of hitting this 100 times, it will become 10 times. Because from here to here is 5 meters. I can go like 100 times in 1 minute, okay? But when the volume expands, the distance will also what? Expand. So which means instead of going 100 times in 1 minute, I might now go 10 times in 1 minute. You now see the container will do what? Shrink or expand, depending on the what? Kinetic energy. And collision, frequency of collision depends on the what? Kinetic energy. The higher the kinetic energy, the higher the frequency of what? Collision. You got that now? And the more expansion you experience. Chai. Did that make sense? So, in an exam, I say, explain Charles' law using kinetic theory. You must first of all tell them, increase in temperature leads to what? Kinetic energy. Okay? Which increases frequency of collision of gas particle with the walls of the what? Container. Leading to what? Increase in volume. Is it not simple? It's very simple. Because by the time you mention kinetic energy, you are telling them that you know that those particles possess what? Kinetic what? Energy. And that's why they are what? Moving. So let us not waste time on this nonsense point. Yes, it's not a high yield. You might not even see it in exam. It's maybe for knowledge sake. I don't even know what to use. You do with the knowledge itself. Can someone know you back? I thought I don't want to be the only person. Sir, instead of going straight to the point, sir, are you invariable saying that our boiling kettle expands in volume whenever much pressure is applied to it when boiling. Please answer me, sir. How many circuits here ever? Please learn how to be concise. It helps. If in official settings now, over the weekend, maybe high volume, Odobia, it will read the shorter ones. So here, let me explain something. In kettle, is it expansible? No. This law will not be obeyed. What I mean now? Because I was using expansible. What would I? Let me use okay, observation balloon. Do you know what is observation balloon? Eh? Okay, you don't know. Okay, don't worry. If you go home, go and buy observation balloons. It can cost you like $1 million. It's a small money. Now, is there another thing? See, please, don't allow me to waste time here. It's not necessary. But let me answer this question. Here, the container is what? Expansible. You know what I mean by expansible? It's elastic. It's elastic. If you apply pressure, it will do what? Expand. Just like when you are inflating a balloon, is it not expansible? Yes. When we are inflating a kettle, is it expansible? It's not obey this law now. Okay? It can only obey other laws, which we state now. But do you know why you will know that your kettle is obeying this law somehow? When you cover it with a lid, you know what is a lid now? The cover of the kettle. If the cover of the kettle is free, what will happen? What is it telling you? That the volume is what? Increasing. You want to get now? So let's leave it there. But in other sense, we are not doing expansivity. Because in expansivity, once you apply heat in any material, in most material, they will do what? Expand, okay? But now, we are not interested in the particles of the container. We are only interested in particles of the what? Gas. Because if you are looking at the particles of the container, please, I'm digressing a bit. Okay? But let me understand my direction of digression. See, if you get that, just look at it very well. Are you seeing it? The container has its own particles. Akuma. Sim yes, can this so you are not confused? Now, the container contains another particle, which is the what? Gas. Our interest is in what? The gas particle. But if you look at the particles of the container, like the container is solid, okay? The particles of the container, once you heat them, they will also what? Expand. Because if you heat any particle, you are increasing the kinetic what? Energy. And once you increase kinetic energy, they will move faster. They will occupy more space. They will do what? Occupy more space. So, the particle of study here is that of the what? Gas. But in actual sense, the kettle is also what? Expanding. But that expansion is not as a result of the what? Gas. So, in conclusion, that kettle system is not obeying what? Charles' law. Of course, you know why. The material is not what? That means it's not elastic. Okay? We are done here. understand this, we're going to go Uganda. Please, if you're asking, just know that we don't have time. Make your question concise. Or you give me the question, let's solve it. You're not asking me, another uncle, please, Someone gave me a question on Charles law. I added 273 and I got it. But, hey. I understand this. I didn't see any. Give me the question. Maybe you are trying to tell me that I didn't get that question, okay? That's what I see here. There is no question here. She or he was telling me stories. Bring the question. Don't waste our time. Okay. Boy's law. We are done with this. If you have to solve any question, it's V1. Should I solve an example? Can you solve? Right what? Hello? You guys back email the monitoring. Just guys monitoring. So listen, But I beg you, if you are here with past question, jam, try to extract questions on gas law. It will help us. Do you understand me? So that I will not be forging question anyhow. So the volume of a gas at 50 degrees Celsius is this, okay? First of all, you establish the initial situation. That is V1 and T1. Establish the initial what? Condition. So initial condition is used to be the first parameters, which means the volume of the gas is V1, okay? 20, Abi. Why the T1 is what? 50 plus what? 273. Don't use that 50 raw. No. You must add what? 273. You must. So what will it give you? 3 what? Now, you now look at V2. What is V2? 40. Okay? When it's double, then you're not looking at what? T2. So you see that vital to any equation is to identify the what? The parameters. Okay? Now you can apply the law. V1 over what? T1 is equal to what? V2 over what? T2. Do I need to solve? I had a man mathematics, Evan. Are we? See stuff, yeah? I think we are through with Charles' law now. Boy's law. He says that volume is directly proportional to what? Inversely proportional to what? Pressure. See, again, I want to explain this in a kinetic theory, no longer the ordinary theory. Do you understand me now? So any law we are looking at, let's look at it kinetically. Now, if you say Boyle's law, they all start with what? Volume. Do you see it now? So it means that volume and pressure are what? Inversely related. Volume of a gas is inversely or indirectly proportional to what? Pressure. Meaning that inverse means as this one is increasing, the other one is what? Decreasing. Unlike Charles' law. So here, how can we explain it in a kinetic form? What is constant here? Now look at it. You have a volume of a container. You can change the volume. That is, it is still elastic now. If you want the walls of the container to be stiff, remember what I told you that according to kinetic theory again, that the pressure of a gas is the collision with the walls of the what? Container. No collision with the with one another. So which means the one we count is the one is collide with the what? Container. And how do you know that the container pressure is increasing? By touching it up here. By do what? If it is stiff or rigid, what does it mean? That the pressure is what? High. But if it is flabby up here, the pressure is what? Low. So it means that for you to know that there is increase in pressure, first, the container wall will be what? Rigid. Now, if you have a constant mass of a gas, this mass is 10 kilograms now. Now, I will now shrink this container. The same number of particles, so what will happen? Do you understand what is happening now? Negative. This volume is high up here. But the collision with the walls of container, is it often or less often? Here is what? More often up here. And the more frequency, the more what? Pressure. Because the pressure is how often is it colliding with the walls of the what? Container. So which means here, the distance to travel to collide is high. While here is very, very what? Small. So which means they will collide with the container more often, making it what? Stiff. Do you understand me now? So the more you decrease the volume, you are increasing the what? Pressure. You want to tell me, Kita? Here, we don't consider the temperature. It is at constant temperature. Constant means that if this temperature is 20 degrees Celsius, this one is also what? 20 degrees Celsius. We are not increasing the temperature. It is constant. But we are changing the what? Volume. So which means if you shrink the volume, the walls will be what? Harder. Where? That's it. Just like you want a balloon now. You see, no? Okay, yes. After inflating the balloon, you tie it up here so that you no longer put more air. So you notice that if you try to reduce the volume of the balloon, what happens? Pressure will do what? Increase up here. Pressure will increase. But if you touch the walls of the balloon, it will be what? Hard. That is pressure. But if you try to increase the volume, it will be what? Flabby, Abby. Telling you that the pressure has what? Decreased. So which means the higher the volume, the smaller the pressure. One year also. One. So saying that this is what is, it means that V1 P1 is equal to what? What of graphical representation? Graphically. Yeah? Yeah, can be. Question, yes. Yeah, but can you go? Nah. Okay, somebody brought a question, sir. But you'll be the one to solve this one. Yes. Because this is volume and pressure, Abi. Yeah, you will solve this one. Look at this thing now. We have that V, and we have that V is equals to K over what? P. Yeah? I'm trying to explain something. Just look at what I'm doing. And we also say that V can be K times 1 over what? P. Or whatever. You feel me? Inverse. I can say V and what? P. Or what? Because it means that at high V, pressure is what? Low. At high P, volume is what? Low. What again now? So when volume is high, pressure is what? Low. Do you know there can be confusion now? Let me introduce confusion. I'm trying to introduce what they introduced. What if I plot this over this? Huh? It becomes what? Is it inverse or straight? Huh? Somebody is still saying inverse. You know, I can only explain this if you understand mathematics a bit. Do you understand? If you do what? Mathematics a bit. Because from here now, this and this are now 1 over P. Eh? That is, I didn't say P. What did I say? 1 over P is non-directly proportional to what? V. But P is what? Indirectly what? Proportional. You don't understand? You know, this and this, are they the same? Here, V is directly proportional to what? P. But now V is directly proportional to what? 1 over P. Do you understand it? No. Which means this one will go what? Straight. You hear me now? It will go straight. I'm if you an exam. That's why at times they will say which of this graph represents what? Boy's law. Ou follow get the peak in Kedo. Okay, if you get send about. We have the one at 1 over P. Eh? We have the one without what? 1 over P. You have what? 1 over P. Take note. So, I think we are done with Boy's law. What else don't you understand here? Is it the example? You can listen. You explain using kinetic theory. Okay? I'm doing 3 things in each of these law. 1, using kinetic what? Theory. Okay? Number 2, graphical representation. Secondly, example. So you solve this one. The pressure on hundreds. Because if you are giving us question, give us the options there. What's a meaning? Do you see the question? Can you see it? Can you solve? 1 minute. Okay, 50 seconds up, yeah? Yes, jam is 50 seconds. Aye. Just try and get. Make mistake. I don't even see myself teaching this. I thought all of you know this. Hello? First of all, initial condition, okay? Just know that Boy's law is what? P1 V1 is equal to what? P2 V2. Just, you must know this one. You can forget other ones, but you know this one. Our P1 here is what? Eh? Our V1 is what? Okay. P2. Is it 100 or 1,000? Okay, 1,000. For Julia can know. And we are looking for what? V2. See, this is the first thing you must write. If one mistake, people will never jump. Like, but if you master it, fine. First of all, write down your parameters somewhere. Because if you are doing sharp, you might misplace it. You will just waste the whole 1 minute. Because you won't see the answer. You start again. By then you are becoming nervous. So the first of all, make sure you identify the word parameters. Then you start placing it. And look at our formula here. That is 750 times 100, okay? Is equals to 1,000 V2. Simple. 750, Abby? Abby? CM cube. Eh? Once again. Before I go here, let me finish the law first. But do you understand Boy's law now? Pressure law. So pressure law means P. Do you see it now? Increase in temperature leads to what? Increase in what? Pressure. Should we explain it kinetically? Okay. Here, you just know that, of course, it's clear here, knowing that once you increase the temperature or heat, what happens to the movement of a particle? Eh? The kinetic energy will increase, okay? Yeah? That means the motion will become more energetic. Therefore, the frequency of collision with the walls of the container will do what? Increase. And whenever the frequency of collision with the walls of the container increases, what happens to pressure? Pressure will do what? Increase. That's what we mean. Just know that there is link between heat and what? Temperature. Then linking to kinetic what? Energy. Whenever you increase heat or temperature, kinetic energy will do what? Increase. And whenever kinetic energy increases, frequency of collision will do what? Collision. Frequency of hitting the walls, that is colliding with the walls of the container, will increase. And once you are colliding with the walls of the container will either expand or become more stiff. Okay? That is pressure. So, which means increase in temperature, increase in what? Pressure. Meaning that P1 over T1 is equal to what? P2 over T2. You know how this thing come about? This particular one? Because Fonde go, hey, what is the problem? Fonde go mathematics. Eh? When you make this one subject of the phone, what do you have? Constant, okay? It means that in this law, that P over T is always going to constant. It can never change. Meaning that P1 over what? T1 is all equals to what? P2 over T2. Because P over T is always the same. You should give it the same thing. It's even equals to P3 over what? T3. Constant. Okay. It remains how many laws now? 2. Before we go to general gas equation. Of course, the graph to this one is simple, okay? P increases with what? T. Abi? It's a straight line, okay? One, again, the most important law here, very important, aside general gas equation, is Graham's law of what? Diffusion. Hey. I waste time here. I waste serious time. Depending on your response. Because this one, you must understand this one. Unless you are a Down syndrome. Yes. So if you are a Down syndrome, please come front. This is rate of what? Diffusion. That means R is equal to V over what? T. Time. So it means that we are looking at the rate at which the gas is diffusing. You know what is diffusion? Eh? Now, different gases, they move. I can roughly, do you know in physics, you can just say diffusion is just mixing of gases or huma. Yes. Somebody can say diffusion is what? Mixing of gases. Because they are natural mix, you know, not the one you mix by yourself. No. Because the gases, they mix because they can move up, yeah? If they cannot move, can they mix? No. If they cannot move, there will be no diffusion. So diffusion means that the gas particle, they possess kinetic what? Energy. They are moving. That's why they can move from one point to another. But they move from where they are more to where they are what? Less. Now, the rate of that movement, which you can call diffusion, depends on how heavy or lighter heavy or light the gas particle is. Do you understand what I mean now? The heavier particle, the movement will be what? Sluggish. Okay? The lighter one will move faster. So it means the lighter gases diffuse faster than the what? Heavier gas. That is conclusion now. And that's why we are using in that law, they use density. They use what? Density. Of course, you know what is density? Eh? Okay, now. The denser a gas, it means that the gas is heavier. Opposite of lighter. Okay. Should I define diffusion again? What is diffusion? Movement of particles. Full stop. What's it go? What's it go? Okay, now. If I have a porous plug now, porous plug like this. Porous means that you know what I mean by porous? Eh? And I have two gases like I have hydrogen and I have nitrogen. Which of them will you see here first? Eh? I want to understand what I mean. I have two gases here. Maybe this one is 20 liter. This one is also 20 liter. I mean, after 2 sec, I might get 15 liter here of hydrogen, and I might get 5 liter of what? Nitrogen here. You know why? What is the atomic mass of nitrogen? 14 up here. What of hydrogen? Do you see hydrogen is lighter than what? Nitrogen. Which means nitrogen will diffuse less up here. That's why at the same time, 15 liter of hydrogen pass. Why 5 liter of nitrogen what? Pass. That's what Graham is telling us. That the rate of this, because the rate of this diffusion is now 15 over 2 up here. That is rate here. Volume of again time. Y rate here is what? 5 over 2. If you get so rate of hydrogen here, knowing that rate is equals to volume over again time, is equals to 15 over what? 2. Y here is what? 5 over what? 2. So this rate is 7.5 okay? Liter per what? Sec. While this one is what? 2.5 liter per sec. Second. That's what I mean here. You see what you call rate of diffusion? Eh? So you see, the rate of diffusion of hydrogen is higher, 7.5, than rate of diffusion of what? Nitrogen. Why? Why? Because the density of nitrogen is more than that of what? Hydrogen. That is the explanation of this law. But don't mind this law. Eh? I just summarize it. That's why it is in this form. But before I move on, do you understand us? If you know that you do not understand us, I didn't add a minus in any way. Minus quoi? It's already answer question. Okay, you say I should state. Some of you think that we are saying kindergarten. Akwatam kaina akwado. Eh? Do you know that I have stated Graham's law here? Do you know? Don't worry, let me state it. Sister? African Hamburg sister, I was a sister in a mail. Do you see Graham's law here? Eh? It means that rate of diffusion is inversely proportional to what? Square root of the what? Density. Of course, we are still going to expatiate more because density depends on mass, okay? So we are still going to state it in another form. But first of all, understand what we are trying to state. We are trying to tell you that here, that rate of diffusion, which is R, okay, will be more when the density is what? Less. Like the density of hydrogen here is what? 1. That of nitrogen is what? 14. Assuming, okay? So you see, the lower the density, the higher the what? Rate of what? Diffusion. The higher the density, 14, okay? The lower the what? Rate of diffusion. And it's stated here. Though we put square root. Square root is, don't bother yourself about the square root. Look at what's happening, okay? The main thing that is happening there is that it is an inverse word proportion. That when this one increases, this one will do what? Decrease. When this one decreases this way, just like if I put it this way, is it the same thing? So if I put it this way, it means that when this one increases, this one will do what? Increase. But that's not what it is. This is what it is. Okay? Okay. Do you understand? If you don't understand, make again. Close your eye. Or stand up. To see you now. I want to know how many of you. But don't worry. I will not repeat it. You understand in the process of examples. As you know. Now let me restate this thing again. Instead of considering only one gas, Graham did what we call comparison. Do you understand me now? In that comparison, we are now comparing two gases now, like we did here, for better understanding. Okay? Now, if I have gas 1, I can also have what? Gas 2. Which means, if I say that R1, or let's say R hydrogen now, is 1 over, is it not the same thing with that? Okay? It's same thing by saying R2 D2. That is, if you know mathematics now, it's still inverse. Do you understand me now? It's still inverse. The opposite of it is if I had said that R1 over R2 is equals to D1 over what? D2. It means that all of them are what? Direct proportion. Do you understand me now? It means that R1 increases to what? D1. R2 increases to what? D2. But to tell you that you are not a science student, not just an art student studying mathematics, they make it complicated in this form, where this is inverse, since they are not occupying the same what? Position. Okay? It means that increase in R2 leads to what? Decrease in what? D2. So we are comparing two gases. It's the same thing by saying R2 is inversely proportional to what? 1 over what? D2. It's the same thing. Because, okay, let me do it mathematically. Should I? Should I? If I say that R1 if you divide both sides, you will have 1 over D1 over again 1 over what? D2. And from what I know about mathematics, if on a time I had the law, whenever you have fraction in a fraction, denominators will do what? Move. Okay? That's how you do it, to be very simple. Here, if you have fraction in a fraction, to simplify it, always move the word denominator. Here, denominator will move up, denominator will do what? Move down. That is to say, A times what? C over what? B times D. If B came down up here, Y C what? Moved up. I'm giving you instances so that you not ask me a question what I will do here. You're telling me now. Just like saying half over half. It is same thing as what? 2 over 2 up here? 1. Because 2 will go down, 2 will do what? Go up. So what am I doing here? Denominator will do what? Move. This one will move down, this one will do what? Move up. So what do I have? D2 over what? D1. What again? So this is Graham's what? Law. So we are not able to finish Gauss' law today, Sha. But you know, even if you don't understand it, don't worry. When we finish it, you understand.